Imagine 100,000 tons of iron roaring across the rails, a structure so massive that the ground begins to tremble miles before it arrives. Machines that are not measured by the number of cars they pull, but by the miles of steel they stretch across the landscape, cutting through the terrain like horizontal skyscrapers in motion. Mechanical structures so heavy they can reshape the logistics of entire continents, capable of dragging the weight of whole cities through some of the most hostile deserts on Earth.
Today, we are not talking about ordinary locomotives. We are talking about the engineering of endurance. Welcome to Colossal Scale. Today, we are going through the 9 levels of the longest and heaviest trains that have ever challenged the laws of friction. Subscribe, hit like, and get ready for Level 9. Because the final giant on this list is so long that you could cross an entire city before the train finishes passing.
Level 1. The Iron Train, Mauritania. We begin in the heart of the Sahara, where engineering faces one of the deadliest environments on the planet. Here operates the Iron Train, a roughly 1.5-mile-long megastructure that is the direct result of an ambition born more than a century ago, back in the early 1900s, when locomotives like the Virginian AA tried to become the first steel skyscrapers on rails. Today, in the middle of the desert, convoys of more than 200 cars can be seen moving the wealth of an entire nation. What makes this structure colossal is its absolute resistance to wear in conditions that destroyed the giants of the past. In a place where iron dust and fine sand would grind down any conventional engine, these locomotives have been modified to breathe filtered air and operate under a sun that can reach around 122 degrees Fahrenheit. It is a moving bunker that does not stop for sandstorms or for the absolute emptiness of the desert, and it proves that the engineering of persistence has perfected the brute force that inspired the first massive steel locomotives. But there is one detail that humanizes this enormous metal beast. Its cargo is not only ore. Thousands of people travel for free on top of the exposed mountains of iron, facing the wind, the heat, the dust, and the open sky, turning the train into a nomadic city that crosses the desert every day. It is the definition of survival engineering, a giant that refuses to surrender to nature. But be careful, because allowing a human operator to handle a train in the Sahara is one thing. Letting artificial intelligence take full control of a steel monster in the Australian desert is something else entirely. Level 2. Rio Tinto Autohaul, Australia. In the red, forgotten lands of Western Australia, engineering meets artificial intelligence to create something without precedent. Rio Tinto Autohaul is a roughly 1.5-mile-long convoy, and it holds the title of the largest mobile robot in the world. Unlike any other train on this list, this megastructure has no driver on board. It is controlled by a digital brain located more than 930 miles away, coordinating every movement with extreme precision. The technical achievement here is the management of inertia. Moving a structure of this size without a human being inside the cab, without someone physically feeling the vibrations of the rail, requires a network of laser sensors and military-grade GPS systems constantly monitoring the tension in the couplers. The Autohaul system must calculate in real time how to brake and accelerate a mass of steel that takes miles to react. It has to prevent the train's own force from tearing it apart or throwing it off the rails on the curves of the Australian desert. This autonomous giant represents the end of the purely mechanical era and the beginning of the digital era at full industrial scale. By eliminating human error and fatigue, Rio Tinto has managed to make this megastructure operate 24 hours a day, 365 days a year, turning it into an endless conveyor belt of iron ore. It is a vision of the future, where colossal machines no longer need us inside them to conquer the most difficult terrain on the planet. But be careful, because letting a computer drive a train through the desert is one thing. Pushing a 2-mile steel monster into one of the densest and most dangerous jungles on Earth is another challenge entirely. Level 3. The Carajas Train, Brazil. Now we move into the density of the Amazon rainforest, where the giant of the company Vale operates, the Carajas Train. With a length of just over 2 miles and a formation of up to 330 cars, this megastructure is responsible for moving one of the purest iron reserves on Earth. Crossing the jungle with a machine of this weight requires reinforced railway infrastructure capable of supporting pressures that would sink a conventional road into tropical mud. The true engineering of Carajas lies in its distributed traction system. For a structure nearly 2 miles long to avoid breaking under its own weight, the locomotives cannot be placed only at the front. They are positioned at strategic points throughout the convoy. This allows the train to push and pull at the same time, balancing the stresses across the entire formation and allowing the Iron Serpent to climb and descend slopes without the middle cars collapsing under the accumulated pressure. Visually, the Carajas train is a moving wall that seems to have no end as it snakes through the Amazon foliage. It is a masterpiece of logistical engineering, connecting the depths of the jungle with Atlantic ports and moving in a single journey what thousands of trucks could not carry in a month. But do not get comfortable, because the next level takes us to Africa, where the train does not only transport energy, it generates it.
Level 4. The Coal Freight Giant, South Africa.
Across the plains of South Africa, we find one of the most efficient megastructures on the planet, the coal export train of the Richards Bay Line. Reaching about 2.3 miles in length, this giant regularly moves more than 40,000 tons of cargo. However, its size is not the most impressive part. The truly extraordinary part is how it uses physics in its favor to help power the country while fulfilling its mission. The crown jewel here is regenerative braking. As this megastructure descends the slopes of the South African mountains, its inertia is so brutal that the locomotive motors act like enormous generators. Instead of burning through brake pads, the train converts heat and motion into pure electricity, injecting megawatts of energy back into the national grid. It is a mobile power plant that helps pay for itself. From an engineering standpoint, this level teaches us that massive scale can also become efficient. The challenge for South African engineers was designing an electrical system capable of withstanding the extremely high currents generated by a train almost 2.5 miles long without melting the overhead lines. It is a feat of circular engineering. The weight of the coal helps generate part of the energy needed to move the next load. But generating energy is simple compared to the challenge that comes next. How do you move a massive structure in a country where people barely fit inside the trains or even outside them?
Level 5. Super Sheshnag, India.
Forget everything you know about railway power. In India, scale is measured first in people. We have all seen the almost unreal images of trains disappearing beneath a human tide, with passengers hanging from doors and covering the roofs as if the laws of physics no longer applied. It is this absolute chaos of saturation that forced engineers to create an extreme solution, the Super Sheshnag. This megastructure is not a conventional train. It is an experimental formation almost 2 miles long, born from the union of 4 massive trains into one seemingly endless Iron Serpent. What makes this level so unusual is that the Super Sheshnag exists to save a system standing on the edge of total collapse. By moving this steel giant, India can clear the tracks of heavy freight trains and free up space for the thousands of passenger convoys that move an entire nation. It is an emergency engineering response, a moving wall almost 2 miles long, designed so that commerce does not stop while millions of people saturate the rest of the network. It is the point where freight volume meets human volume in a constant battle for space. To prevent this monster from tearing itself apart, engineers use a wireless control system that synchronizes the locomotives distributed along its full length. Visually, the contrast is brutal, and it is necessary in order to understand the scale of the problem. We go from the chaos of people hanging from local trains to the absolute precision of a steel line that seems to have no end. The Super Sheshnag proves that in a country where density is law, the only way to survive is to build structures that challenge every known scale. But if you think coordinating almost 2 miles of steel in the heat of India is difficult, get ready. Because the next level takes us to a place where metal becomes brittle and the air itself freezes.
Level 6.
Canadian Pacific, Canada. In the imposing Rocky Mountains of Canada, the enemy of engineering is not weight, it is extreme cold. Canadian Pacific freight trains regularly exceed 2.5 miles in length, winding through mountain passes where a single mistake can become an ecological disaster. The challenge here is keeping a steel megastructure operational when temperatures fall low enough to make metal brittle. The great technical achievement at this level is the compressed air braking system. On a train 2.5 miles long, air takes a long time to travel from the cab to the final car. And under Canada's Arctic cold, moisture inside the pipes can freeze, blocking the brakes and leaving the giant without control. To prevent this, engineers install air repeaters and intermediate locomotives that act like additional lungs for the structure. Visually, watching this 2.5-mile steel serpent cross suspension bridges surrounded by snow is one of the most powerful images of human scale. It is a constant battle between friction, gravity, and ice, where only intelligent energy management allows the cargo to reach its destination. But now we are going to raise the level again, because in the United States, scale is not only measured in length, it is also measured in height.
Level 7. BNSF double stack, United States. This is the level where the megastructure becomes three-dimensional. BNSF trains in the United States can reach 2.5 miles in length, but what makes them truly unusual is their double-stack design. While much of the world loads one container per rail car, American engineers redesigned tunnels and bridges across an entire country to allow cars to carry two containers, one on top of the other. The result is a wall of steel almost 20 feet high, moving at up to 62 miles per hour. This engineering decision doubled transport capacity without adding a single extra foot of length to the tracks. But it also created a new problem: the center of gravity. To prevent a 2.5-mile train from tipping over in strong crosswinds, the cars use a well-shaped structure that lowers the containers as much as possible, bringing them almost down between the rails. Visually, the double-stack train is colossal scale at its highest logistical expression. Watching one of these trains pass is like watching a 2-story building move in front of you for several uninterrupted minutes. If we placed all of its cargo onto trucks, we would create a traffic jam more than 6 miles long on almost any highway. It is the ultimate infrastructure holding up the mass consumption of a nation. But no matter how tall this wall of containers becomes, it is still small compared to what happens when the Australian desert decides to stretch steel to limits that seem to challenge the curvature of the Earth.
Level 8. BHP Ore Train, Australia. We return to Australia, but this time we are here to witness the heaviest and longest regular operation on the planet. The ore trains of the company BHP operate every day with lengths reaching more than 4.5 miles. This is not an experiment. This is the daily routine of a megastructure transporting the iron that builds the cities of the world. At this scale, the train stops behaving like one solid object and starts behaving almost like a fluid. The engineering challenge here is called shock force dynamics. Because of its length of more than 4 miles, the front of the train may already be braking while the rear is still accelerating. That creates internal shock waves that could tear steel couplers apart as if they were paper. To control this beast, engineers use power management software that handles each locomotive independently, absorbing the tensions before they become destructive. Standing beside this giant as it passes is an experience that changes the senses. The sound is a constant roar that can last almost 10 minutes, and the mass of metal is so enormous that it seems to generate its own microclimate of heat and wind. It is the practical limit of what steel and friction can withstand in daily operations. But there is one more level, a single moment in history when we decided to break every rule.
Level 9. The absolute record. BHP Iron Ore.
Finally, we reached the ceiling of global railway engineering. On June 21, 2001, in northwestern Australia, the longest land-based moving object humanity had ever seen was assembled. A train more than 4.5 miles long, made up of 682 cars and moved by 8 locomotives distributed along its body. It was a mass of 100,000 tons of iron. That is comparable to the weight of a Nimitz-class aircraft carrier, but stretched out across the rails. The technical feat was an experiment at the limits of the possible. A single driver, assisted by a state-of-the-art remote control system, had to start this monster from a complete stop, applying a pulling force so immense that the rails strained under the effort. The train was so long that because of the curvature of the Earth, the driver could not even see the first quarter of his cargo. It was a structure that occupied the entire horizon. This record has not been surpassed in more than 2 decades because it represents the physical limit of materials.
The inertia of 100,000 tons in motion is so enormous that stopping this train required miles of distance and surgical precision to avoid overheating the braking systems. It is the ultimate monument to human ambition, a steel serpent more than 4 miles long that proved that when it comes to colossal scale, the sky, or the length of the track, may be the only limit. Australia's record appears to be the physical boundary of steel and friction, but for cutting-edge engineering, rails are only the beginning. While today we are amazed by these iron serpents, inside the world's technology development centers, the next evolutionary leap is already being designed. Freight Hyperloop, a megastructure that would abandon air resistance and physical contact, sliding cargo capsules through vacuum tunnels at more than 620 miles per hour, eliminating the barriers of weight and time forever. Wow! But if you want to see the true future of colossal scale, we have to look toward heavy freight maglev. We are not talking about conventional trains. We are talking about magnetic levitation platforms that, because they do not touch the rails, could allow the creation of convoys with lengths we would consider impossible today. Structures of steel and magnetism so massive they could connect entire continents, operating like a global conveyor belt that never stops, powered by clean energy and pure digital precision. Are we reaching the limit of what we can drag across the Earth? Or are we about to witness the birth of a planetary transport system that redefines our geography? The answer is in the hands of the next generation of engineers. If this escalation of titans blew your mind, subscribe and hit like so you do not miss our next mega construction. And if you are passionate about extreme machines, you need to watch our video about the largest structures in the world right here. We will see you in the next colossal scale.